Vale, vamos a comenzar en 3, 2, 1. Buenas tardes, bienvenidos al seminario del Departamento de Química. Agradecemos a la gente que nos está acompañando de manera presencial en el Salón de Seminarios R206 y a través del enlace en YouTube. Antes de presentar a la ponente del día de hoy, tenemos unos anuncios para ustedes. Van a aparecer en la pantalla. Y bueno, los invitamos a que visiten la página web de las conferencias y si quieren participar en los seminarios o enviar sus comentarios al correo que está en pantalla. De seminarios somos los responsables, el doctor Víctor y un servidor, doctor Edgar Carrera Crespo. También los invitamos a que visiten la página web del Departamento de Química y envíen sus comentarios o quieren participar en los podcasts al correo que aparece en pantalla, de los que son responsables el doctor Ricardo Peralta Ávila y la doctora Lucero González Sebastián. Y también los invitamos a que envíen sus comentarios o participaciones a la Gaceta Tlecachil, de la cual los editores y responsables son el doctor Humberto Laguna Galindo y el doctor José Luis Córdoba Frunz. Y también los invitamos a visitar los enlaces que tenemos en YouTube, Facebook, X y la página web del Departamento de Química. Y ahora sí, seguimos con la presentación de la ponente del día de hoy. Vamos a leer su semblanza. Y es la doctora Melissa Ramírez. La doctora Melissa Ramírez obtuvo su título de licenciatura en Química en la Universidad de Pensilvania en el 2016, donde trabajó como asistente de investigación bajo la supervisión del profesor Gary Molander. En el 2021 recibió su título de doctorado con especialización en química orgánica en la Universidad de California, con sede en Los Ángeles, California. Sus asesores de doctorado fueron los profesores Ken Hook y Neil Gard, con quienes realizó estudios sobre la reactividad de intermediarios cíclicos rígidos y de reacciones pericíclicas para síntesis de moléculas complejas. Actualmente, la doctora Ramírez ocupa una posición postdoctoral presidencial en Caltech en el laboratorio del profesor Brian Stoltz, y su investigación es financiada por la National Science Foundation bajo el programa MPS ASCEN y el National Institute of Health bajo el programa K99/R00 Mosaic. El tema que nos presenta el día de hoy la doctora Melissa Ramírez es Computations and Experiments in Synergy, Reaction Development and the Establishment of Predictive Computational Models. Adelante, doctora Ramírez.
Muchas gracias por esa introducción y muchas gracias a todos por estar pues ahí en persona. Me gustaría haber podido estar ahí también en persona, pero pues por Zoom es algo muy emocionante también. Y entonces voy a hacer el screen share. Aquí está. A ver. Bueno, ¿sí pueden ver bien aquí?
La presentación.
Sí, sí lo pueden ver.
Sí, la vemos.
Ok, qué bien. Ok, muy bien. Bueno, muchas gracias. Y como fue mencionado, ahora voy a hablar sobre los estudios que he hecho en las áreas de Experiments and Computations por Reaction Development. Pero antes de empezar, pues, o platicar sobre la ciencia, quería compartir con ustedes un poquito más sobre mi background y de dónde vengo, mis raíces. Bueno, yo soy pues soy la primera en mi familia que ha ido al colegio. Mis papás son de México y yo nací en Los Ángeles. Mis papás nacieron en Guanajuato, en un rancho que se llama Botija, en el Valle de Santiago. Y pues aquí están mis papás. Mi papá aquí está a la derecha, inmigró a los Estados Unidos como en en the 1970s. Y mi mamá, bueno, ella también llegó a los Estados Unidos con mi papá ya después de un tiempo. Mi papá tenía solo 16 años cuando inmigró a los Estados Unidos y llegó a Pasadena, California, que viene siendo donde estoy ahora, donde está localizado Caltech. Entonces, mi papá cuando inmigró, trabajó por muchos años en un restaurante en Pasadena, limpiando y cocinando. Mi mamá cuidaba, aquí está mi mamá, y pues mi mamá cuidaba a personas ya mayores, ancianos, en una casa de retiro. Y pues ellos trabajaron muy duro para que yo y mis hermanas tuvieran oportunidades mejores que lo que ellos tuvieron. Entonces, yo y mis hermanas, pues fuimos nacidas en Los Ángeles. Aquí estamos los cinco. Aquí están mis papás y aquí estoy yo en medio y mi hermana la mayor y la menor. Y somos cinco y aquí estoy yo aquí hay fotos de mí cuando pues yo estaba, siempre vivía en Pasadena hasta que llegué a la high school. Bueno, en el 2012 fui la primera en mi familia en graduarme de la escuela secundaria. Mis papás solo habían llegado al segundo grado. Ahí en el rancho donde vienen ellos, pues no tuvieron la oportunidad de estudiar este, más de ir a la escuela secundaria. Y pues fui la primera y fue un logro muy grande, la primera de terminar la high school, pero pues seguí adelante y decidí a ir a la Universidad de Pensilvania. Pues no fue solo de decidir, ¿verdad? Porque pues siempre nos cuesta mucho poder tener oportunidad y buscar y encontrar, porque no siempre, no todos podemos, pero muy agradecida estoy de poder haber tenido la oportunidad de ir a la Universidad de Pensilvania, que es ahí en la Universidad de Pensilvania, este, recibí una beca que se llama el Gates Millennium Scholarship y por esa beca que es parte de una fundación que tiene Bill Gates, um, tuve la oportunidad de ir al colegio sin tener que pagar nada. Entonces fue lo que se llama un full ride scholarship a Penn. Y cuando estuve en Penn, realicé mi interés en la química orgánica y tuve oportunidad de hacer estudios en el laboratorio de Gary Molander. Aquí está una foto de mí en el laboratorio en como el 2015. Y me gradué ahí de UPenn en el 2016. Aquí están mis papás, pues estuve muy orgullosa de poder terminar. Aquí me aseguré de tener los colores de la bandera mexicana. Y después de UPenn, pues UPenn está al otro lado de los Estados Unidos. Es un vuelo de 6 horas de Los Ángeles a UPenn, que está en Philadelphia, Pennsylvania. Pues me regresé a California para mis estudios doctorales y decidí ir tuve la oportunidad de ir a UCLA para mis estudios doctorales. Y allí en UCLA tuve interés en hacer mi doctorado en química orgánica. Tuve dos supervisores, uno en la área de Synthetic Organic Chemistry y el segundo supervisor fue en la área de Computational Organic Chemistry. Aquí estoy. Cuando terminé el doctorado, era el año 2021 y fue durante la pandemia. Después de terminar en UCLA, fui a Caltech, donde estoy ahorita, para cumplir mis estudios de postdoc. Y en Caltech he tenido oportunidad de ser parte de un programa que se llama el Caltech Presidential Postdoc Program. Aquí estoy yo con otros que están en este programa en Caltech y este programa apoya a personas que vienen de diferentes grupos que no son bien representados en la ciencia. Pues yo como latina y primera pues en mi familia de ir al colegio, y luego mis papás que vienen pues no, nunca tuvieron, no tuvieron el financial status para poder apoyarme en mis estudios. Entonces también eso es algo que no tiene buena representación en las ciencias. Entonces, pues este programa ha sido muy importante en mi éxito aquí en Caltech y pues lo que les quiero comunicar es que siempre, yo creo que todos sabemos esto, pero es bueno recordarse de que pues la curiosidad y perseverancia, pues de veras pueden servir como motores de desarrollo en lo que sea que queremos hacer en nuestros estudios. Para mí fueron motores en mi desarrollo como química orgánica en estas áreas de síntesis y computación. Y bueno, en Caltech soy parte del laboratorio del profesor Brian Stoltz. Y pues Brian, aquí está a la izquierda. Esta es una foto del grupo en el 2022. Yo estoy aquí en medio, un poquito cansada, pero ahí estaba. Y una segunda foto aquí del grupo un año después de la primera. Brian está, no lo veo al Brian, aquí está. Brian, aquí está, profesor Stoltz, y yo estoy aquí atrás. Y en el Stoltz Lab en Caltech, pues hay muchas oportunidades pues, primeramente es un grupo de síntesis. Y nos enfocamos en las áreas de reaction development y total synthesis of natural products. Y bueno, el grupo es muy grande, como les enseñé en las fotos ahorita, hace un momento. Aquí hay unas fotos de los estudiantes en el doctorado trabajando en el espacio, aquí en el laboratorio. Bueno, también tenemos espacio de oficina. Lo que les quiero hacer, o explicar aquí es que pues hay muchas oportunidades aquí en el Stoltz Lab, aquí en Caltech, y si tienen preguntas ustedes después de este seminario o si yo puedo ayudar en cualquier forma, me pueden contactar. Aquí está un QR code que si solo lo escanean con el celular, aquí eso los lleva a la página de web del Stoltz Laboratory en Caltech. Pero ahí está mi email también en caso de que quieran contactarme. Y entonces, pues en UCLA, mis supervisores fueron los profesores Ken Hauk y Neil Gard, y luego ahora en Caltech es Brian Stoltz para mis estudios del postdoc. Y ahora voy a explicarles pues lo que estudié durante mi tiempo en UCLA y lo que estoy haciendo ahorita en Caltech. Um, Empezando con los estudios que he cumplido en UCLA. At UCLA, I developed or was trained as a synthetic and computational organic chemist. Um, my PhD studies focused on demonstrating the utility of strain cyclic intermediates in the synthesis of complex molecular scaffolds. So, for example, these strain cyclic intermediates included azacyclic allenes, which are shown here. Typically, you don't have an allene in a six-membered ring. And so these are highly strained. And while many people thought for a long time that these were not valuable in organic synthesis because they were so reactive, we demonstrated using computations and experiments that these cyclic allenes can actually be controlled to build valuable scaffolds in a controlled manner. And so because I was trained in these two different areas of synthetic and computational organic chemistry, I had the opportunity to work on a variety of projects during graduate school. These are four examples of different projects that I was able to contribute to while at UCLA. What I'll say, because due to time constraints, I won't share the details of each one of these different areas and what we learned. What I'll say overall is that because I have this interdisciplinary skill set, I've been able to use, for example, my computational skills to collaborate with groups outside of UCLA in order to provide computational insight on reaction mechanism to experimentalists. And so with that, for today, what I'll share is the work I performed in demonstrating the synthetic utility of cyclic alkynes and arynes in accessing these products, polycyclic aromatic hydrocarbons, which are quite valuable in materials chemistry. And so focusing on this specific area, we looked at accessing these polycyclic aromatic hydrocarbons, and polycyclic aromatic hydrocarbons have had a remarkable impact on the field of materials chemistry. These compounds are widely employed in devices such as organic light emitting diodes, organic photovoltaic devices, and organic field effect transistors. A attractive quality or feature of these molecules is the rapid evolution of their electronic properties with increased conjugation. And so there's quite a bit of interest in developing chemical methods to synthesize a wide variety of these polycyclic aromatic hydrocarbons. However, at the time when I was in graduate school, and I think this can still be said today, there are some challenges associated with synthesizing highly functionalized polycyclic aromatic hydrocarbons. In particular, the synthesis of these compounds typically require harsh reaction conditions, such as elevated temperatures, harshly acidic conditions, and organometallic reagents, as shown in this example. Furthermore, most methods, or many of these methods to make the polycyclic aromatic hydrocarbon compounds are limited with respect to only being able to access or enabling only the access of symmetric products. It's highly desirable to develop methods that allow us to access non-symmetric polycyclic aromatic hydrocarbons, because then we would have access to a greater variety of these compounds for testing with respect to their desirable properties. In the 1970s, Steglick and coworkers had demonstrated that benzene and an oxydiazonone can be taken together in a reaction to generate the corresponding pyrrole intermediate here. This is not isolable, and instead react with the second equivalent of benzene to generate this 9,10-diphenylanthracene. And so this is a very neat example from the literature, because it demonstrated the ability to use benzene to access these polycyclic aromatic hydrocarbons. Now, something to note here is that benzene is generated in situ, and I'll talk about that in a minute. But this is a strained intermediate that is generated during the reaction. While this was great and was really quite interesting chemistry, this was still limited to the synthesis of symmetric products. And so it'd be desirable again to access non-symmetric polycyclic aromatic hydrocarbon products. In 2019, my coworkers in the GARG laboratory disclosed a report demonstrating the ability to use cyclic alkynes rather than an arine to access non-symmetric polycyclic aromatic hydrocarbons. And so just to note, again, this cyclic alkyne is generated in situ, and I'll share with you what the precursor to this strain intermediate is. But that being said, piperidine can react with a differentially substituted oxydiazonone to generate the corresponding pyrrone intermediate after dinitrogen extrusion. This pyrrone can be isolated and then carried forward in a separate retro-Diels-Alder reaction to generate with a different strained intermediate to generate now this product having 4 quadrants of differentiation. The ability to access these products that are non-symmetric hinges on the ability to isolate this pyrrone intermediate. And so while this was a step in the right direction, it was still unclear as to why this cyclic alkyne varied in reactivity when compared to an arine, such as a benzene. And so really there were key mechanistic features of this transformation that remained poorly understood. And this is where I stepped in to provide computational expertise to provide insight on why there's these differing reactivities of arines versus cyclic alkynes in this chemistry. Now, with respect to how this reaction works, we had a proposed mechanism in mind. The proposed mechanism is shown here. We start with an oxydiazonone, and then our first strained intermediate equivalent reacts with this starting material to generate this bicyclic system that then would undergo retro-Diels-Alder reaction to extrude dinitrogen and generate this pyrrone intermediate. This pyrrone intermediate would then react with a second cyclic alkyne or arine to generate this lactone that would then undergo retrodeoxygen reaction to extrude carbon dioxide and generate the final product. The key mechanistic questions we had here were with respect to the differences in reactivity of benzene versus the corresponding cyclic alkyne. That would be one. This would be a cyclohexane. So these two were directly compared. So first mechanistic question was, how do the reactivities of these two strained intermediates differ in this first Diels-Alder reaction? And then what are the corresponding reactivity differences of the corresponding pyrones generated in these reactions? In answering this question, we started by comparing again the reactivity of, or investigating the reactivity of benzene in this reaction manifold. And here, so before I walk through this result, what I'll highlight is that this silotriflate in the GARG laboratory, we typically used a silotriflate as a precursor to a given arine or cyclic alkyne. The way this works is that you have cesium fluoride in the reaction, and cesium fluoride is it has poor solubility in acetonitrile, the solvent in this reaction, and so because there's because it's not completely soluble, we have a slow incorporation of fluoride in the reaction mixture. And so because of that, you can have slow generation of your arine. So as soon as the fluoride is incorporated in solution, fluoride adds to the silane, and then you have elimination of this triflate group. And this can be done slowly. Now, in this particular experiment, we hypothesized that using an excess amount of the oxydiazonone would allow us to generate the corresponding pyrone. And again, this was desirable because if we have a pyrone intermediate, we can then incorporate a different strained intermediate in a second separate reaction. And unfortunately, we weren't able to generate this pyrone. Instead, we generated the 9,10-diphenylanthracene product where two equivalents of benzene are incorporated. And this is done at room temperature. So it's not because it really, we didn't heat this reaction up. And so given this result, we still kept in mind the potential to test this reaction now with the corresponding straight intermediate, which would be cyclohexane. And again, we generated cyclohexane now using the corresponding silotriflate precursor. And in this experiment, analogous reaction conditions demonstrated now the ability to generate the corresponding pyrone intermediate in a 75% yield, and this what I'll call double addition product in only a 4% yield. And so what this highlighted now was this, again, what this further highlighted was the differing reactivities here between these strain intermediates. And it was quite exciting that we could isolate this pyrone because we could explore its reactivity in chemistry with other strain intermediates. But still, nonetheless, this brought up the question of why is this pyrone, I'll refer to this as a benzopyrone. Why is a benzopyrone intermediate not isolable experimentally? To gain insight on this, we performed a computational analysis, and with respect to the computations, I incorporated density functional theory using the ML62X functional for geometry optimization in a small basis set, and then performed single point calculations with a larger basis set and with inclusion of solvent. The free energy profile for reaction involving benzene and the oxydiazonone was initially evaluated. And based on these computations, reaction of benzene with the oxydiazonone has an energy barrier of 10.1 kcals per mole. This is an exothermic reaction. And subsequent retrodeoxygen reaction leads to the key benzopyrone intermediate. This occurs readily. The barrier is only 5.3 kcals per mole. But now, quite notably, this benzopyrone reacts with a second equivalent of benzene through a barrierless process. This is highly exothermic. And this lactone then undergoes Retro-Diels-Alder reaction to generate the final product and release carbon dioxide. Now, going back to the question that we had with respect to the inability to isolate this benzopyrone intermediate, to answer the question of why this is not isolable in experiments, it's important to hone in on the two Diels-Alder reactions here. And what we can note here is that as soon as this benzopyrone is generated in the reaction, it reacts with another equivalent of benzyne, meaning that this benzopyrone outcompetes the oxydiazonone for reaction with benzyne. And so because of this, this benzopyrone cannot be isolated experimentally. It's more reactive than the oxydiazonone toward reactions with benzyne. This is in contrast to the reaction involving cyclohexane, where here I've shown the analogous free energy profile. And rather than walk through this entire free energy profile, I'll just cut to the chase and really point out that in order for us to understand why, in this case, this pyrone, which I'll refer to as an alkyl pyrone, this alkyl pyrone is isolable in experiments because if we look at the two Diels-Alder reactions, we focus in on these. The initial Diels-Alder reaction now involving cyclohexane and our oxydiazonone has an energy barrier of 11.5 kcals per mole. But now this second Diels-Alder reaction involving our alkyl pyrone and cyclohexane now has an energy barrier of 16.1 kcals per mole. So what this means is that this pyrone no longer competes with the oxydiazonone in reactions with the strain intermediate. We can have initial reaction between these two components. This occurs more readily without having competition of this subsequent Diels-Alder reaction, which has a higher energy barrier. So as a result of these differences in the energetics now of these two Diels-Alder reactions, and what this means is that we can isolate the pyrone and use it in subsequent chemistry. Looking more closely at the reactivity of this pyrone, with respect to experiments, it's still quite valuable to have this pyrone, and we explored the synthetic utility of this pyrone by incorporating a variety of strained intermediates. The strain intermediates incorporated included arines leading to these initial products shown here. We use an excess amount of the arine in this second reaction. And again, while I did not note it here, these reactions work well. These reactions were performed at room temperature. Additionally, cyclic alkynes can be incorporated in the second reaction to provide access to the products shown here on the bottom half. Furthermore, this chemistry can provide access to a variety of polycyclic aromatic hydrocarbons varying in functionality on all four quadrants of the products. So what I mean by this is that initially we can take the silotriflate precursor, the cyclohexane, and a differentially substituted oxydiazonone, and perform the first reaction here to generate the corresponding pyrone intermediates, and then perform a second reaction with now the silotriflate precursor to benzyne to generate the corresponding products shown here in this table. And so this is quite neat and really valuable with respect to now generating these anthracene analogs or anthracene precursors, given that you just need to oxidize this third ring, really having these products with diverse functionality. One of my favorite parts of this project or of this area of research was in demonstrating the utility of this chemistry in accessing more highly conjugated products. So, for example, we were able to take advantage of this alkyl pyrone and perform a Diels-Alder retro-Diels-Alder reaction with this benzyne precursor. So this reaction provides access to this silotriflate product. So only one end of the reaction partner reacts with our pyrone. This does require a bit of an increase in temperature, not quite much at 30 degrees. This cyclotriflate intermediate can then be carried forward in a second reaction with this pyrrone at room temperature to generate the corresponding tetracene precursor in a 65% yield. We refer to this as a tetracene precursor because you just need to oxidize this fourth ring in order to arrive at the tetracene derivative. Additionally, we can use this cyclotriflate intermediate to access a pentacene precursor. In this reaction here at the top, we used an excess amount of the pyrrone relative to the cyclotriflate, and at room temperature over 12 hours, we were able to access a precursor to a pentacene analog. Again, given that you just need to oxidize these last two rings to get to the pentacene product. The synthesis of this pentacene precursor can be achieved in a one-pot reaction that combines our key alkyl pyrrone directly with our bis-benzyne precursor. So this cyclotriflate would be generated as an intermediate, and you can then directly arrive at the corresponding pentacene product through reaction of the cyclotriflate with another equivalent of the pyrrone. And so at this point, I've been able to share with you a major component of my doctoral studies at UCLA, where I was co-advised in both computational chemistry and in the areas of computational chemistry and synthetic organic chemistry to provide computational insight on the mechanism of reaction between strained cyclic intermediates and oxidizinols to arrive at polycyclic aromatic hydrocarbon products. And furthermore, in the laboratory, I demonstrated the synthetic utility of this approach to accessing a variety of new anthracene analogs and extended polycyclic aromatic hydrocarbon frameworks. And so at the end of my time at UCLA, I was excited about switching gears for my postdoctoral studies. Here's a map showing where UCLA is here on so this is the general LA area, Los Angeles area. Los Angeles is pretty big and pretty spread out. So UCLA is here. This is the molecular sciences building where I worked. This is a picture of a central part of UCLA's campus here. This is called Royce Hall. And so I decided to, or I was able to go to Caltech, the California Institute of Technology, for my postdoctoral studies. As you can see here, the drive to Caltech at this, I don't remember when I took this picture, this takes 50 minutes. It says here to get to Caltech, which is in Pasadena. And so getting to Pasadena, not very far, but this was quite meaningful to me, not just because of the science, and I'll talk about the science in a moment, but because Pasadena is where I grew up. Like I said, both of my parents, mis papás llegaron a Pasadena in the 1970s. And so I grew up in Pasadena. I went to high school there. And as a postdoc at Caltech now, I've been able to return to my high school chemistry class, for example, and do outreach there to help increase interest in chemistry in the sciences. This is me in my high school chemistry teacher's classroom. And then I've also been able to bring students from the local community. These are middle school students that I brought into Caltech to show them around the laboratory space in the Stoltz lab. Also, this is the front of the building where our lab is located. And then lastly, I've been able to also mentor students at Caltech, undergrads who get to do research for the summer, for example. And so with that, another thing I did point out, and without going on a tangent, my dad worked at Caltech for some time at the dining hall as well, and so it's quite a privilege to be able to now work in the laboratory space. Whereas while his work was valuable, the work that he did is valuable. He didn't get to choose whether he cleaned the dining hall or whether he got to learn chemistry in the laboratory. That wasn't a choice he had. So it keeps me grounded, and really it shapes the leader and scientist that I am today. And so with that, in terms of the science, at UCLA, as I just mentioned, or as I focused on in the last couple of minutes, I focused on combining experiments and computations to develop chemistry to access these frameworks that are more or less flat. And this has value, but these molecules don't have a lot of three-dimensionality to them. And at Caltech now for my postdoc, I've had the incredible opportunity to develop skills both in experiments and computations, but now in the area of asymmetric catalysis. Asymmetric transition metal catalyzed reactions in particular to access spirocyclic lactones. And so before I delve into the specifics of the chemistry here, I'll focus on the products that we're accessing through this reaction development that we have focused on. These products are spirocyclic lactones. Spirocyclic lactones are prevalent in a number of pharmacologically relevant small molecules. These are some examples of valuable molecules in the pharmaceutical area that contain a spirocyclic lactone structural unit. Something that you'll know is that this corresponds to the gamma spirocyclic lactone structural unit. That being said, lactones themselves are synthetically useful because they can undergo ring opening reactions with retention of stereochemistry, and so that's very important here. But now, if you look here at the top right, the alpha spirocyclic lactone structural unit, in particular, has been largely underexplored in the pharmaceutical industry. A big reason for this is because there's a limited number of methods to make these, and that makes a bit of sense. This is challenging because you have this quaternary carbon center now, and that in itself is something to access or to build. That's something challenging to access a quaternary carbon center. Given this gap in the literature, we sought to fill in this gap in the literature by taking advantage of nickel catalysis. In particular, we envisioned taking a given lactone bearing a pendant aronitrile and using the conditions that we would develop after acidic hydrolysis allow for generation of the corresponding spirocyclic lactone product. In this area of research, I've had the opportunity to work and mentor undergraduates and graduate students in the laboratory, and so these are project partners in this particular area, and so each one of these are members of the Stoltz group. That being said, we had, in developing the chemistry that I'll walk you through in a bit, we had drawn inspiration from a serendipitous result from a former postdoc in the group, Dr. Masaki Hayashi. So Dr. Hayashi was a former postdoc and had worked toward developing an alpha arylation reaction of lactams. In this particular experiment, he had taken this lactam and this aryl chloride, and using the conditions that we have here after acidic hydrolysis, anticipated generating this alpha arylated lactam, but quite surprisingly instead generated this alpha acylated lactam. Again, this was unexpected, but the group switched gears at this point and focused on optimizing this reaction, leading to this alpha acylated lactam. And that is shown here as a summary where the Stoltz group disclosed a report in 2016 where we were able to combine a variety of lactams and aronitriles to generate the corresponding acylated lactams. But really, what a big question you may have here, and that I certainly had when I first looked at this chemistry, is how does this reaction work? There's multiple components in this reaction. We have nickel cod, the chiral ligand, base, and then there's bromobenzene and lithium bromide. What is the role of these two things? And so this is where it's important to look at reaction mechanism more closely. In this report, the group had put forth a proposed reaction mechanism. That reaction mechanism or catalytic cycle is shown here. So I'll walk you through this. It was proposed that the reaction would involve this nickel zero intermediate with the ligand bound onto the metal, the chiral ligand. Oxidative addition with bromobenzene would lead to this nickel 2 intermediate, and subsequently, ligand exchange and nitrile addition would involve this lithium enolate of the lactam, given that there's LHMDS in the reaction, and the corresponding nitrile to generate this nickel-bound imine and to liberate lithium bromide. So this is just one arrow that represents this ligand exchange and nitrile addition. Subsequent reductive elimination would regenerate the active catalyst and release the amine shown here, and acidic hydrolysis would provide the final product. Now, while this was a good starting point with respect to understanding reaction mechanism, there were still key questions that remained unanswered. The first question was with respect to what is the mechanism of nickel catalyzed nitrile addition? How do we generate this carbon-carbon bond? Here, there's just one arrow that represents ligand exchange and nitrile addition. But really, it does not provide insight on how the carbon-carbon bond forming step works. The second question was, what are the origins of enantioselectivity? Why is this reaction enantioselective? And that goes back to understanding this carbon-carbon bond forming step. And then additionally, what are other enolates other than this enolate derived from the lactam, and electrophiles other than this aeronitrile that can be incorporated in this reaction platform? And so this is now where we have really focused on answering these questions through the development of an enantioselective alpha spirocyclization of lactones. With respect to reaction development, initially we've worked toward developing this chemistry by using a model system, this model substrate. This is a lactone bearing a 1 carbon tether between our lactone and the aeronitrile. Given that I'm keeping track of time, I'll go ahead and summarize the results here. What I'll say is that quite interestingly, when we use nickel cod as our nickel 0 source and the initial chiral ligand here, so that's BINAP, LHMDS as base, and bromobenzene, this is in toluene. And after acidic hydrolysis, we were able to obtain a 79% yield of our product and a 38% and in 38% EE. So this was a good starting point. The reaction, the selectivity definitely needed work, but this is a good starting point for developing this chemistry. Ultimately, when we compared this this first entry with these 3 additional entries where we tested the reaction with these other ligands, what we found is that the TUN-phos ligand here, this diarylbisphosphine ligand, provides product in 74% yield and now with 48% EE, albeit providing the opposite enantiomer of the product. So this was good. It's 48%. But now we tested the Mandy-Phos chiral ligand, Mandy-Phos ligand class, where these Mandy-Phos ligands are ferrocinol ligands, where we have these amines on the backbone of the chiral ligand. In this first entry, the parent Mandy-Phos ligand contains these phenyl groups on the phosphines themselves. This ligand provided product in a 78% yield and 78% EE. This was great. There was a 30% increase in comparison to the previous result I shared with you with respect to selectivity. In summary, really, these 4 different Mandy-Phos ligands, out of the 4 Mandy-Phos ligands I'm showing here, the 2 that were best performing were the Mandy-Phos ligand with just the phenyl groups on the phosphines, and then the Mandy-Phos ligand now containing xylyl groups on these phosphines. Those 2 results provided product in good yield, and the selectivity was 78 or 81, depending on the ligand. So this was good, but still a question we had was how do we increase enantioselectivity here? what if the EE here is in 95 or 99? How can we get there? And one question we had was with respect to potential background reaction. What's the background reaction here? We considered the ability to have a lactone, our substrate, and the potential to have LHMDS lead reaction with LHMDS lead to racemic product. So this would involve deprotonation of our lactone, direct addition of the enolate to the nitrile, protonation, and then acidic hydrolysis would lead to racemic products. But quite notably here, this reaction, when we combined our substrate with the base after acidic hydrolysis, we only obtained a 3% proton NMR yield of this product. So that meant that the background reaction was not a problem. That's not why we had selectivity at 78 or 81. So we went back to the two best results we had. These are the results I just showed a moment ago. And we raised a question of what are solvent effects on enantiomer selectivity? When we switch from toluene to tert-butyl methyl ether, so still nonpolar, but in this case, the yield increases a bit, but the selectivity is still pretty much the same. Something important was the fact that when we introduce a coordinating solvent, THF, or a polar solvent, dioxane, the selectivity drops drastically. This reaction is almost not selective when we introduce these types of solvents. So a natural question became, now in this case, what is the effect of solvent on the background reaction? Again, perhaps the solvent increases the rate of background reaction. What I mean by this is we have the substrate and base, and perhaps we generate racemic products in greater quantities if we change the solvent. But here, it looked like when we incorporate these other solvents, the background reaction is still pretty minimal, only providing product in only 1 to 3%. So that was not a problem here. That's not why the selectivity is lower. And so this further highlighted the importance of understanding the effect of solvent on the nickel catalyzed transformation itself. And this is now where I've drawn from my skills in computational chemistry to model this reaction. Here is a proposed catalytic cycle. Again, we have oxidative addition, but now in this case, we can think about ligand exchange a bit more closely or carefully to generate now this oxygen-bound enolate. Nucleophilic addition would generate the key carbon-carbon bond. So addition of the enolate to the nitrile would lead to this intermediate, which would then undergo reductive elimination to provide the imine that would then be hydrolyzed. But what's to say that this oxygen-bound enolate, what's to say that this enolate isn't a ion pair instead? This is important to really look at closely because it impacts carbon-carbon bond formation in this nucleophilic addition step and how we understand the origins of enantiomer selectivity. So key questions we had here are, what are solvent effects on reaction mechanism? And then what are the origins of enantiomer selectivity again? And so this is where computations have really been a critical component of this research area. Now I'm keeping track of time and we're almost at 50 minutes. So I'm just going to go ahead and kind of give you a summary. I won't be able to share with you the computational analysis that we have at the moment, given the time constraints. So I'll just go ahead and move a couple slides forward. I'll share with you really what we've been able to demonstrate back in the laboratory with respect to the utility of this reaction and the types of products we can generate. But if you have any questions on the computational analysis, I'd be more than happy to answer those at the end of this. In the laboratory, we've been able to demonstrate that this reaction allows us to generate these spirocyclic scaffolds. These first 3 entries demonstrate the ability to generate these five-membered ring here with variation of electronics. So we can incorporate an electron donating or withdrawing group when we look at the aeronitrile component. And then we've also tested this reaction where we increased the length of this tether to generate a 6-membered ring. And quite quite notably, the selectivity decreases. This is something that we're investigating computationally as well. The lactone itself, we can increase the size there and generate product and with good selectivity. The yield decreases, but that's a result of undesired ring opening and decarboxylation in that reaction. That reaction or that result is shown here. So we generate the product in 27% yield, 79% EE, and this byproduct is generated as well. This is the byproduct that results from, again, ring opening of the the six membered ring, and then decarboxylation leads to this product here. And so keeping that in mind, that's something that we're working on, changing the acidic hydrolysis for. We think this is a problem with the hydrolysis step itself. And one of my favorite parts in this area has been in demonstrating the ability to generate 7-membered rings using this chemistry with high selectivity. When we generate the parent 7-membered ring here, the product is generated with 90% EE, which is awesome because typically 7-membered rings are difficult to generate with high stereo selectivity. We can incorporate electron donating or electron withdrawing groups. And interestingly, introduction of this trifluoromethyl group leads to a decrease in selectivity that we're still looking into computationally as well. And so in terms of what I've been able to share with you in the second component of today's talk, I have performed experiments and computations toward developing a nickel catalyzed spirocyclization reaction of spirocyclization reaction of lactones. In terms of future directions, we're still focusing on further gaining insight on the mechanism of this transformation using computations and further investigating the scope of this transformation with respect to both the lactone and aronitrile components. And so I just want to say thank you to all of you for being here today, in particular as well to my postdoc advisor, Brian Stoltz here, as well as the Stoltz group. The names highlighted here are individuals I've had the opportunity to work with on different projects during my time here at Caltech, as well as the staff at Caltech for keeping things running smoothly, as well as my PhD advisors, Professors Ken Hauk and Neil Garg. This is a Hauk group in 2021 when I graduated. Here's Ken in the middle. This is a computational organic chemistry group. Here I am. And then at the top here is the experimental group I worked in during graduate school. This is Neil Garg, and here I am again in 2021. These particular individuals that I had the opportunity to work with on different projects during graduate school at UCLA, my collaborators during graduate school, as well as my thesis committee at UCLA, and lastly, these organizations for funding. And these organizations that I've had the opportunity to give back to the community through. This is something that, again, keeps me grounded and reminds me of the importance of giving back to others and being there for the people around me as much as possible, really paying it forward. So whenever I can. So with that, thank you all again for being here today, and thank you for the invitation to speak. I would be more than happy to take any questions. Gracias.
Gracias, doctora Melissa Ramírez, por compartirnos parte de su investigación y bueno, por la presentación. Y ahora pasamos a la sesión de preguntas. Igual invitamos a los que nos están siguiendo por el canal de YouTube que hagan las preguntas por el chat. Adelante, ¿alguien tiene pregunta? Adelante, profesor.
Professor Melissa, could we ask in Spanish? Is okay?
Sí, en español está bien. Hablo pues español y inglés, pero como de seguro ya se han dado cuenta también el Spanglish, o lo que sea, aquí estoy, como sea.
Una pregunta al doctor Ricardo Peralta.
Hola, muchas gracias por la presentación. Está muy interesante, sobre todo que investigaste grupos, electrowitroen, o sea, que le quitaban electrodensidad y también con grupos donadores.
Sí.
¿Investigaste también la selectividad con grupos voluminosos? No
Oh,
sé,
sí.
ajá, no sé si eso afecte también la selectividad.
Sí, entonces, como un butyl group, por ejemplo, ¿no? Algo más grande. No, la respuesta ahí es no. Los grupos que hemos introducido aquí es como también como el methyl group, um, pero no, grupos como el terbutyl group no hemos investigado. That would be a great opportunity in terms of investigation.
Una pregunta técnica. ¿Qué modelos de solvente utilizan para el modelaje de las reacciones?
Sí, aquí en esta área de I didn't have enough time, like I said, to share with you the computational results, but we have used the SMD model for the single point calculations.
Ok, ok, gracias.
Sí.
¿Más preguntas?
Bueno, si no, tenemos una pregunta del chat. Vamos a verla. El doctor Ignacio González pregunta, ¿Did you correlate the solvent acidity properties with the dose of intermediates to synchronize the reactivity?
Can you repeat that again? I'm sorry.
Ah, ok. Ok. Bueno, sí correlación. Bueno, se la digo en español.
Okay.
Sí, sí correlacionó la acidez de las propiedades de la, sí correlacionó la acidez del solvente con las de los intermediarios para sintonizar la reactividad.
No, no, pero eso puede ser pues es buena idea de hacer, no lo he hecho.
Ok. Gracias. ¿Alguna otra pregunta aquí del público presente? ¿No? Ok.
Bueno, yo solamente quiero agradecer que la profesora Melissa aceptó esta invitación, aún estando a distancia. Fue muy ilustrativa desde el punto de vista de su carrera profesional, pero también que ha pasado a lo largo de su vida sobre los retos que pudo haber tenido y que ahora pues es una profesora exitosa. Muchas gracias por la participación.
Gracias, muchas gracias por la invitación y si tienen preguntas después de ahora, lo que sea, pues mi email está en el website, entonces como sea, I would be more than happy to help. Thank you.
Ok, doctora Melissa, bueno, muchas gracias por la presentación. A continuación vamos a presentar la constancia por el seminario que nos impartió. Y bueno, el Departamento de Química de la UAM Iztapalapa le otorga la presente constancia a doctora Melissa Ramírez por impartir dentro del ciclo de seminarios del Departamento de Química del trimestre 24I la conferencia Computations and Experiments in Synergy, Reaction Development and Establishment of Predictive Computational Models. El día 27 de marzo de 2024 firman el doctor Jorge Garza Holguín, jefe del Departamento de Química, y el doctor Juan Edgar Carrera Crespo, coordinador de seminarios. Muchas gracias por la presentación, doctora Melissa.
Gracias, muchas gracias por la invitación.
Ok, bueno, pues también agradecemos a los que nos acompañaron de manera presencial en el R206 y de manera virtual en el canal de YouTube. Buenas tardes, somos Departamento de Química, somos UAM Iztapalapa, somos Panteras Negras. Hasta luego.
Que hubo comentarios en YouTube que no se leyeron.